Okay. Johanna is a third-year PhD student at Stanford, advised by Keith Winstein. Her work focuses on frameworks for serverless computing, and she's promised to give a very important, earnest talk today.
Hi, everyone. Today, I'm going to present our research on computation-centered networking. This is a joint work by me and also my wonderful colleagues from Stanford University and Princeton University. So to begin today's talk, we'd like to start with three things which seems unrelated to each other, but we promise that there are actually a common reason behind them.
So hi, I'm Cecily.
I'm Gwen.
So Gwen, I absolutely love your hot nuts paper. How did you make figure 3? I'd really like to reproduce it.
Happy to help. I pushed everything to a Git repository.
I see a lot of files and folders, but how did you actually generate this figure?
I forget. It's weird how Git is so good at storing files and folders and their compositions, but none of the computational relationships.
What if Git can also remember computational relationships?
Hi, I'm Jeff Bezos.
I'm Merriman.
Our customers love AWS Lambda, but it seems silly that their code spends 90% of its time idling the CPU, waiting to fetch data from elsewhere. They're wasting our infrastructure.
Can we cleverly schedule functions to run on the same nodes as their dependencies?
Not really. We don't know the dependencies up front. Their code just fetches whatever it wants after it starts running. And my good man, these customers pay us for every millisecond until the task completes. We'd lose money if we made them finish faster.
What if AWS sees a dependency and is actually incentivized to finish up sooner?
Hi, I'm Jack.
Hi, I'm Prism.
Man, AWS Lambda is really bumming me out. My function spends 90% of its time waiting on I/O, and I have to pay for that time.
What do you expect? It's an unpaid program to them. They can make it faster. Also, why would they? The longer it takes, the more you pay.
I guess I'm paying them for the wrong thing then. What I really care about is getting the correct answer to my function call. I don't even care if it's Amazon or whoever does it, as long as somebody reputable stands behind the results and there's recourse if they make a mistake.
What if customers actually pay AWS for results, not effort? So we just presented three things, and we think that the problems in the three things are the results of an under-constrained notion of network computations. And in today's talk, I would like to propose on our solution, computation-centered networking, and how we sketch the framework to implement it. So when we are saying computation-centered networking, what we really mean is that the primary job of the network services is actually to provide answers to computations. For a system to be able to track the computational relationships between applications, all the applications should expose itself to the underlying system. Then for users and service providers to be able to pay and bill by computational results, there needs to be a pre-existing, pre-agreed, verifiable common notion of correctness. This is also the case for a version control system, such as Git. If the users would like to ask the system why a file contains the content it does, and be assured that the reply is actually correct. Then for a cloud platform to be able to optimize for locality and for a reproducible computational pipeline, we're arguing that computation should be separated into I/O and compute, such that all the dependencies of the computation are explicit even before the computation starts, and the compute itself is actually deterministic. So this computation-centered networking idea is actually about an end-to-end argument of computations, where we require that systems should be accountable to a high level correctness of the computations while gaining the agility to decide where and how to complete the actual computation. And from the three things we presented at the beginning of the talk, we've summarized three principles for computation-centered networking, which is fine-grained visibility into application data flow, an objective common notion of correctness, and a separation between I/O and the compute with all non-determinism delineated. So to realize this dream, we designed our framework for computation-centered networking, FixPoint, which I will introduce later. This is actually these three principles motivate the initial design of FixPoint. Looking at these three principles, the first question would be, how are we going to represent all these data objects? So in our solution, we're bringing blobs and trees from Git. Then the second question would be, given these data objects, what would be the way of describing computations on data? For this purpose, we designed a low-level language we call Fix that I will present later in the talk. And then the question would be, given these kind of orientations, what is the actual notion of correctness here? To make all the computations reproducible in a FixPoint, we blend all the computations by a deterministic WebSumming modules. So fixed point centers around fixed. This is a low-level lightweight language that describes computation of data. In this system, a opaque object ID is assigned to each object. And there are three kind of primitive objects in the system, which is a blob, that is a vector of byte, tree, which is a vector of names, and a thunk that refers to a computation by its name. Using these primitive types, Fix is able to present computations as an encode, which is a tree in a special format. And in this encode, there will be several entries, including a resource limits, which govern the runtime execution. Then there will be a procedure represented as a blob, then all the other dependencies that should be available to the function during the execution time. One very simple example to start is the actually add function that adds up two integers and generate a new integer. Then there are actually three major components to the computations, which include the add function itself and also the two inputs. Then by giving these three major components and construct the encode of it, we're able to construct encode that represents the computation itself. And this will be evaluated to a blob as its output. So Fix is actually able to represent many different kinds of computations that are much more complicated than a simple add function. For example, for a Python interpreter, it will take in probably some command line arguments, including like a path to the actual script to run. So that can be encoded as a tree in the encode. And then it will probably also take in like a representation of a file system to operate on. And that can be represented actually as a Git repository at a certain commit. Then in the output, there will be basically blobs that contains the return value of the main function, the standard out, the standard error, and probably also a Git repository and a newer commit, which encapsulates whatever changes have been made during the execution time. Computations are also able to output other kinds of computations in their output. For example, to implement like a map function, in the output, there will be thunks that point to other encodes that basically apply the function to each entry of the tree. All these thunks in the output tree are able to be evaluated in parallel with each other so that this parallel map can be done into a 10,000 parallel execution of all the encodes. After looking at Fix, I'd like to present our initial implementation of FixPoint. As I mentioned before, all the computations are presented by WebAssembly modules in FixPoint. So to actually transform these WebAssembly modules into executable raw machine codelets, we implement our own in-memory toolchain to complete the whole transformation. To achieve this, we have to heavily modify WebAssembly to C, which is a pre-existing tool as part of the WebAssembly binary toolkit. We also implement our own in-memory live linker to link the things against the actual FixPoint API. To give everyone an idea how fast this toolchain is, we carry out a preliminary benchmark that executes computations on a single core locally. So in the benchmark, we compare 6 different 8-bit functions in implementation. Each of them have a different level of isolation and reproducibility. And based on results, we can see that for a simple FixPoint program, it's around 40 nanosecond overhead compared to a virtual function call. And we think that's actually a fair trade for getting isolation and reproducibility. Then for a full process program, FixPoint is actually much faster than vfork and also much faster than running the vfork in a long-running invocation of a record and replay tool. This really speaks to the advantage of using WebAssembly over using MMU, context switching, or tracing all the sorts of non-determinism in the system. One question to be asked is how is this whole scheme actually different from all the previous works, given that there has been a long line of previous works on container frameworks or cluster computing systems. We think that the problem all comes down to the overhead. We need the overhead to be low enough such that users are willing to make every function call in the system to be a deterministic computation with explicit dependencies, and to actually deeply thread this kind of abstractions into their everyday real-world applications. Towards our envision of this computational networking, there are still many work to be done, including, for example, handling non-deterministic I/O as an explicit unsafe encode evaluation, building a high-level language API to allow users to be able to construct parallel maps in a very easy way. We also want to design a visual debugger like Jupyter Notebook such that users is able to construct and investigate computations simply by clicking and dragging fixed objects. And the actual evaluation may happen either locally or being outsourced to some other service providers. We also would like to enable users to be able to outbid their jobs to some other service providers where their results will be insured and they just get the results back and make the decision by the price quote. I also would like to discuss several central hypotheses that we have for FixPoint to be successful. The first one would be such model of separating between LLM and compute is actually widely achievable and non-determinism can be delineated. I have already talked about that. We have future plans of handling all the non-determinism as an unsafe encode evaluation, but we do hope that this kind of scenario is a very infrequent one. Then the third question would be program won't pay a big performance penalty to be running FixPoint. FixPoint definitely had the benefits of making better placement decisions. and also lightweight context switching, but also we are imposing some slowdowns compared to native code. Then the question would be how that actually plays out in a real world application. Then the last question would be whether this kind of increased efficiency is actually mutually beneficial to service providers and users. So to conclude this talk, we're trying to present a computational networking that has a new kind of end-to-end agreement for computations, where system needs to be accountable for high-level correctness while gaining the agility everywhere else. And there are three principles that guide our design of fixed point, which is fine-grained visibility into application data flow, an objective common notion of correctness, and a separation between IO and the compute. So this is the end of my talk. And also Angela is going to apply for a PhD in this coming year. So if anyone here is trying to recruit, please reach out to her. And any question will be welcome. This is like a qualification exam.
Sure. So Henry Burgley from Princeton University. I was just curious, you talked a lot about scaling in terms of performance, like we need to make the overhead really low so we can put large programs on this. In my work, I often work with very large data sets, and sort of a mutation is like a really common thing. So like I do some research and I take my data set, I mutate it. It's no longer in the exact same form, but this is like a many gigabytes or even terabytes data set. And then, you know, a grad student I'm working with is like, could I do that again? I'm like, well, we got to recollect it, do this and that. So I was wondering if you thought about the sort of the scalability of the data, because obviously a Git tree is only good for like small data sets.
I think for example, like the first question would be, is it possible to actually like all the work in this data set is actually sequential in its essence, that it's actually totally impossible to divide the whole data set into like smaller chunks. That's like the real dependencies of the work. Does that make sense?
Yeah, I see. I guess I'm like kind of how you have to access the data set if you could chop up the data set.
I see. So I think even that's the case, I think one very good advantage of fixed point is that if we are able to tell like the size of the data set and the size of the computation before it actually starts, and there's actually a very flexible scheduling decision of like whether moving this data to the actual computation or whether move the computation to where the data are living right now. So I think even if the data set is really big, then we actually may make some like performance gain in terms of like making better scheduling decision to make the computation happen where the data set is actually currently living.
Mm-hmm.
So I think, thanks for the great talk. You had this point that the main technical challenge you're solving is granularity. You're trying to do fine-grained tracking. Why? Why can't coarse-grained tracking suffice with replay? If you have deterministic replay from coarse-grained checkpoint.
I see. So there, I think the question, if I'm understanding it correctly, is about what is like the granularity of data application of data flow, basically. So I think the very initial ideas that are like more or less motivating fixed points that we want to run everyday application. So for example, for like compiling something, like I want to compile a whole large project, to make this kind of computation pipeline actually something that's like useful, that it will be making sense. There's like a say one-to-one mapping from the source code to the object file. That if I'm just like vaguely pointing this whole large repository compiles to like another whole large executable, it may not be that useful anymore. And also, I think there's a question of like this kind of real world application more or less have a over captioning of the actual dependencies. Like it's going to probably rely on pretty large file system, but only touching like part of it. And I think nailing down to like which file is actually touching would be really useful if we are wanting to do something like reproducible or like kind of tracking for the dependencies in the system.
One more question.
Hi, Ayush, University of Michigan. Great talk. I had one question. This is a high level question about, I mean, you require visibility into application data flow. So I'm wondering if like more language, like moving forward, is it a good idea for more language runtimes to provide this visibility? Because I feel we as researchers have to do so much work in order to get any visibility. So would that be a good feature? I mean, I can imagine doing so much more interesting work if all languages exported some API using which I can like export what kind of data flow and control flow is moving through the execution.
So to answer that, I think the answer is more about like, would it be able to generate different kind of language front end? So one reason why we're picking WebAssembly over some other language choices is that WebAssembly is actually a LVM target, which means that there are many pre-existing programs that can be compiled already into WebAssembly. And I think that should also be the case as WebAssembly becomes like more and more developed, like widely supported among more compilers. And then I think the question, that question would be like, given different kinds of language front end, is it possible to like still support this kind of API? So I think one thing that's like special about fixed point is that even if we're actually trying to compile from assembly modules to actual like executable machine code, the thing that fixed point itself as a system really executes are these like raw machine code lists. I think the notion that we're trying to run the x86 or like ARM like as a raw machine code list probably suggests that we're able to run like many different kinds of applications. I mean, because like a raw machine code is definitely something that can be compiled into. Then the major question here would be like how to guarantee the same level of reproducibility and determinism if like the source is not coming directly from WebAssembly module, but from some other sources.
I assume I don't have a time to follow. Okay. Thank you.
Thank our speaker. Our next speaker is Pradeep. Pradeep is a senior researcher at Microsoft Research. He graduated in 2021 with his PhD from MIT, where he was advised by Harry Bollock. And with that, I'll hand it over to Pradeep.
Okay, sorry. All right. Okay. So I'll talk about how we can facilitate fair competition among high-speed traders when financial exchanges actually move to the cloud. So let's look at how financial exchanges work today. The exchanges run a central exchange server. This exchange server produces market data continuously and sends it out to various market participants. These market participants use this data to generate trades. The trades are processed by the exchange server in a first in, first out manner. Major exchanges such as NASDAQ typically run their own on-premise data centers. Market participants can co-locate to these data centers for a premium fee. Typically, high-frequency traders such as Citadel that are competing with each other on speed co-locate with the server. Now, such traders aim to process incoming data quickly and place trades as fast as possible. Facilitating fair competition among such traders is critical for these exchanges to attract these traders. To this end, exchanges have architected their networks to provide equal bidirectional latency between the exchange server and the participants at the microsecond level. These on-premise data centers typically use equal length cables and in-network multicast to achieve equal latencies. So this way, the market data is delivered simultaneously to all the participants and the trades are ordered in the time that they were generated. These two properties together ensure that a faster market participants' trades are ordered ahead of slower market participants, and that a faster market participant actually wins. Now, recently, there has been a lot of interest to move financial exchanges to the cloud. Several exchanges and cloud providers have announced business partnerships to this end. There are several reasons for this interest. By moving to the cloud, exchanges can forego the burden of managing their own data centers and likely reduce their operation cost. Another advantage is that now only a few participants can co-locate with the exchange server. With cloud scalability, a larger number of participants can co-locate with the exchange and engage in such speed trading. However, moving to the cloud remains a dream as of now. The challenge is that it is very hard to achieve fairness in the cloud without replicating the on-premise setup. In particular, unlike on-premise data center networks, it's very hard to ensure equal latency in the cloud. Now, there are many reasons for why this is the case. For example, the wire length of the cables might differ in cloud networks. There might be transient congestion. So it is very difficult to ensure simultaneous delivery of market data in such environments. Recently, there have been a few proposals from both the financial and computer science community that aim to solve the fairness problem in the cloud. So the solutions from the financial community typically involve modifying how trades are processed at the exchange server. Such solutions are intrusive, and as a result, they haven't seen much adoption. Another category of solution involves using fine-grained clock synchronization to achieve simultaneous data delivery. These solutions don't involve any changes to the exchange server. However, there's still a few issues. So the clock synchronized based solutions work as follows. Corresponding to each participant, there's a release buffer. The release buffer is located close enough to the participant such that the latency between the participant and the release buffer is negligible. The release buffers are clock synchronized. And together, they're responsible for releasing the data simultaneously. So in particular, a market data generated at a particular time is released by the release buffers at a later pre-specified threshold. For incoming trades, the release buffer marks a timestamp corresponding to the time the trades were generated. So the ordering buffer then orders these trades based on the generation time before forwarding them to the exchange. So this way, the solution is able to facilitate fair competition. The problem with the solution is that if the network latency becomes higher than the pre-specified threshold, then the data cannot be delivered simultaneously. Unfortunately, latency spikes that are up to a few orders of magnitude higher than average are common in multi-tenant cloud networks. To guard against such latency spikes, we can use a higher delivery threshold, which will result in a higher overall system latency. Such high latency is typically not acceptable. So even with perfectly synchronized clocks, it is extremely hard to achieve simultaneous delivery of market data and provide fairness. So in our work, we asked the question whether simultaneous delivery of data is even necessary for fair competition. So the problem with existing approaches is that they're looking at data delivery and trade ordering independently. However, high-speed traders generate trades directly in response to the market data. So by looking at data delivery and trade generation together, we can indeed achieve fairness even when market data is not delivered simultaneously. So based on this observation, we introduced the notion of response time fairness for speed trading. Formally, response time of a trade is defined as the time it took to generate the trade after receiving the relevant market data. So the idea here is that if there are two trades that were generated using the same market data point, then the trade with a lower response time should be ordered ahead. So in this example, trade from participant 2 should be ordered ahead of trade from participant 1. So such ordering ensures that faster participants' trades are ordered ahead of trades from slower participants. While achieving response time fairness does not require simultaneous data delivery, it is still very hard to achieve. So the problem is that the exchange does not know how a participant generated a trade. That is, which market data point was actually used to generate the trade. As a result, it's very hard to measure response time. So our main contribution here is a new mechanism that allows the exchange to achieve response time fairness without actually knowing which data points were used to generate the trade. So in this example, a solution will order this trade in such a way that regardless of whether this trade was generated using point X, X minus 1, or X plus 1, the same exact ordering will provide response time fairness in all the three cases. So I'll now present a very brief overview of our solution. Later, I'll walk you through a simple example of how our solution works. So the architecture of a solution is similar to that of clock synchronized based solutions. We both have release buffers and ordering buffers. The solution is two-part. The first part is what we call delivery-based ordering. So inspired by the use of logical clocks in ordering events in distributed systems, we introduce the notion of logical delivery clocks. At each release buffer, we maintain a logical delivery clock that tracks the progress of data delivery to that participant. The delivery clock advances whenever any new market data is delivered to the participant. The difference with traditional logical clocks is that the delivery clocks also advance with real time. So this is because for response time fairness, we need to care more than just about causality of events. And the actual time difference between events is actually important for achieving response time fairness. The release buffer marks incoming trades with the delivery clock timestamp at the trade generation time. So the trades are ordered at the ordering buffer based on this delivery clock timestamp instead of using real timestamps. So essentially what we are doing over here is we're ordering trades from a participant relative to the time the participant actually received the market data. I'll soon show you how this relative ordering allows us to correct for latency differences in data delivery to participants. The second part of our solution is pacing of data delivery at the release buffers. The release buffer does not release the market data directly. Rather, it exactly controls how the market data is released to the participant. So the idea over here is that by controlling data delivery, these release buffers can control how these delivery clocks advance. For more details on how we use pacing and why we fundamentally need it, please see our paper. So I'll now walk you through a simple example that shows how we achieve response time fairness without even knowing how a trade was generated. So in this example, there are two trades that were both generated using market data point X. We actually don't know which data points were used to generate these trades. Now, point X was delivered to the participants at different times. So in this example, trade from participant 2 should be ordered ahead of trade from participant 1. Now, let's look at how these events look in the delivery clock domain. So by definition, the delivery clock time at both the market participants is same when point X is delivered to them. Because we are pacing and controlling how delivery clocks advance, with high likelihood we ensure that delivery clock of participant 1 will advance more in duration RT1 than delivery clock of participant 2 in the shorter duration RT2. So what this means is that the delivery clock of participant 1 at the time of trade generation will be higher than delivery clock of participant 2 at the time of trade generation. As a result, with delivery-based ordering and pacing, trade from participant 2 will be correctly ordered ahead. Now let me show you the results for a simple experiment with two participants. The figure on the right shows the latency from the exchange server to the participants. And as you can see, the network latency is extremely variable. So in this example, both the participants respond to every data point. Response time of participant 1 is 12 microseconds for all the trades. Response time of participant 2 is 8 microseconds. We actually don't know these response times. We consider three simple schemes and report the fraction of trades that were ordered correctly. We also report the round-trip latency for the three schemes. The first scheme uses clock synchronization to deliver data simultaneously. We intentionally picked a conservative threshold for data delivery, and there were times when latency goes beyond the threshold. In this case, only 90% of the trades are ordered correctly. Now we take the clock synchronization based scheme for simultaneous data delivery, but we use delivery clock time for ordering trades instead of using the real time. Now, delivery-based ordering helps us correct for latency variation at times when data is not delivered simultaneously. And as a result, the scheme provides better fairness. Finally, we add pacing of market data. With both pacing and delivery-based ordering, we are able to order almost all the trades fairly. Overall, our solution achieves a better latency fairness trade-off. To summarize, simultaneous delivery of market data is not necessary for fairness. We believe our solution can also help achieve fairness in other cloud-based systems, such as online multiplayer games. Another direction to explore might be other types of fairness that might be more applicable to the applications. So with this, I'll stop. Thank you.
That was really good. I have a very simple, dumb question. Why can't you insist upon when the person makes the trade, come back and say in response to with the hash of the information that came in, here's the thing to which I'm responding.
So yeah, the whole point is that we cannot trust our participants to actually tell us how they exactly generated the trade.
No, but they'd be incentivized to, if they have early, so if you look at it, they want to be as quick as possible from when the thing came in. But if they don't have the hash of something later, what's the incentive to?
So they can always lie that, I say they generated the trade using point X. They can always say, I generated using point X minus 1, X minus 2, X
There's no
minus 3.
incentive to do that, because if you say you generate for X minus 1, that delay is much longer, right? So somebody
Yeah,
else.
so how would you order this trade, right? You would say, if this is ordered using X minus 1, say I'm lying, I would get a different response time. And I would say, I would compare it against some other trade that was generated using also data point X minus 1. And then you actually don't know whether, you are placing this trade correctly or not.
No, but is there any incentive for me to make it look like I'm longer in time from when the.
So it depends on data delivery. So there might be cases if you actually place X minus 1 and X, how they are delivered to the participant. In some cases, it might make more sense for you to lie using X minus 1. Yeah.
So one worry that I have with this model is you're assuming a closed world, you have a closed world assumption in an environment that is not closed. So traders don't trade just on market data, traders also trade on news. Reuters exists because of this. How does this achieve fairness for them?
So typically the idea over here is that this external data stream that is there, it's not as latency critical. So even when we look at current systems, They only ensure simultaneous delivery for the market data. This external data stream typically comes in these data centers from outside.
Wait, so I'm a bit confused about this. So current market system, so like NASDAQ, for example, actually precisely says we don't want to give you fairness. If you are a better trader and you spend more money, you get to make better trades. They're not trying to achieve fairness in this regard.
Oh, no. So they're trying to achieve like speed-based trading, right? They are still giving people equal simultaneous delivery, right? So the whole point over there is still like, if you're a faster participant, you got to win. And what I'm saying is like, respect to these external data streams, delivery of these external data streams specifically at the same time is not as important. If you wanted to ensure with our system, you can integrate these external data streams with the real-time market data stream and sort of ensure fairness with respect to this combined stream. But this will again like come at some cost.
Maria Poslak, Princeton University. That was a great, really cool work. I'm kind of confused. I think in similar way with Thor, in that, so like, what's the connection of this with like the Flash Boys and this type of work, like where you are optimizing your network and because of that, you're actually better off, and that's fair to me. And like and also like if Microsoft or like SoundCloud were to actually offer this as a service, what tells me as one of the players that Microsoft is not colluding with some of the players to give them better network?
Oh yeah, so I think there can be an auditing system which can be put in place. So the whole point is that this release buffer is located very close enough to the participant. So we are imagining this release buffer will be located in the NIC or something. So a participant can actually see that, this is the time I got the stuff. This is the time I delivered the information. Now it's actually possible that, if I'm colluding and lying with other guys, yeah, you can actually jump other things. Maybe, I don't know, using some sort of hardware enclaves might be one thing. Another thing we are thinking about is that, where does the exchange run this release buffer or does the cloud run this release buffer, right? So typically if you are an exchange, my guess is you want to be like actually not collude with the people, because actually providing fairness is a great part of their business. That is how they attract people. So the incentives will align that way. I think I actually missed your first question. Can you repeat that?
Oh, we can take this offline.
Maybe we should take it offline.
Okay.
Thank you, speaker. Our final speaker for the session is Bhavana. Bhavana is a second-year PhD student from Rutgers, and her work focuses on distributed systems and networking. So,
thank you for the introduction, Srini. Good afternoon, everyone. So this is a joint work with my advisors, Professor Srinivas Narayana and Professor Badri at Rutgers University. So our work is situated in the context of cloud-native applications. Our goal is to make the server load balancer react to server performance. However, it is not easy. To achieve our goal, we argue that the load balancers must measure and react to the server performance in band. That is, by directly observing the traffic going through them. The challenge is that the high-speed load balancers do not see the response traffic. So one hand is tied behind our back. So our main idea is that we can infer the response latency indirectly. So we use the gap between a request and its follow packet as a proxy for the client visible performance. In the rest of this talk, I'll show you how to do this accurately. Even a simple control loop built on such measurements can significantly reduce the tail latencies. We think there is an important problem space for the community to explore around the in-back feedback control at the load balancers. To set the context, the cloud-native applications today are supported by the server load balancers at the front end. Balancing also occurs between different tiers of the application. Algorithms on the load balancers like maglev mostly aim to balance the connection load across the servers. However, the cloud-native applications today are increasingly granular A functionality is broken into smaller components, typically called microservices. A single user request can hit hundreds of microservices before a response is returned. In the limit, the application think time will equal the runtime of the network in the cluster, roughly like around 10 to 100 microseconds in a cluster. The app performance will become highly susceptible to the low-level system variability. First off, the app runs deep software stacks. And the process scheduling, noisy neighbors, or a congested path could all easily impact the think time of a single microservice. That is, the performance change in a few round trip times, and we need to react to it quickly. A standard techniques to handle variability, like over provisioning and auto scaling, just won't be reactive enough. Instead, we believe that the load balancers must become server performance aware. The load balancers are in a unique position to detect and react to the fast changing performance. But how to make the load balancers aware of the performance? Today, a common approach is to instrument the applications to expose the queuing and error statistics to the load balancers. This is done out of band. It requires application modification and coordination among multiple teams of developers. Load balancer polling the server or mining information from the centralized agent telemetry systems won't be reactive enough. Instead, we advocate for in-band feedback control at the load balancers. Like TCP congestion control, load balancers should measure and react to the server performance directly. If a load balancer has a visibility of all traffic to and from the server, it can easily infer the performance metrics like response latency, packet loss, and so on. However, today load balancers are often deployed in a direct server return or DSR mode. Here, the load balancers does not see responses. This is typically done to save the CPU cycles in the load balancer. How should a load balancer measure the server performance when it only sees one direction of the traffic? In this work, we show how to measure the end-to-end client response latency on a load balancer implementing the direct server return. The reason we chose response latency is because it's known to be a good indicator of the user experience. Also, it captures the variabilities of all the components involved in serving the request. When a client sends a request to a service, the client visible latency is a time gap between the request and the response. Recall here that the load balancer does not see the response. Our key idea is to use a proxy measurement. If the client sends a packet following up on the response, we can use the time gap between the request and the response to be an accurate measurement of the client's latency. We call the second packet a costly triggered packet. This proxy measurement could be a little off from the client's latency because of the delays at the client between the response and the costly trigger. But it works quite well in many cases. However, every pair of client packets arriving at the load balancer are not costly related. A single client request can be split into multiple packets. In this example, R1 through R3 are part of one request, and R4 through R5 is part of a costly triggered request. It is not easy for the load balancer to detect which packet is costly triggered by a previous one. Our approach is to use the idle periods between the packets. A sufficiently long pause can differentiate the costly triggered packet from the previous ones. But how long a pause? We don't know this ahead of time. For experts on network load balancing in the audience, the flowlet load balancing has a similar issue of finding an idle time gap. In our work, we propose an ensemble technique to identify the right threshold. Over an epoch of time, we use K buckets, each representing latencies according to a threshold on the interpacket gap. We count the number of packets for all the buckets whose threshold is less than the interpacket gap. majority of the inter-packet gap will be counted in multiple buckets. The idle gap will contribute to a few buckets. We found that around the correct threshold, the number of samples experience a steep reduction. We call this a sample cliff. We set this threshold as the idle gap. We provide more details on why the sample cliff method works in the paper. Once we identify the correct threshold, the latency measurement in the next epoch corresponds to the time between two batches of packets separated by this threshold. Using these measurements, we designed a simple load balancing feedback controller that moves traffic away from the high latency server and distributes the traffic evenly across the remaining servers. We built our technique into the open source Cilium load balancer used in container clusters. We run maglev hash function in the load balancer. Our experimental deployment consists of two Memcached servers, front-end by a load balancer. We used Memter benchmark and compared the latency for clients using a latency-aware load balancer versus a standard maglev. In this graph, the x-axis represents the time over which the measurement was taken. Y-axis represents the 95th percentile tail latency observed on the client. So halfway through the experiment, we introduced an artificial delay of 1 millisecond on one of the two servers, whereas the tail latency for the standard maglev load balancer shoots up and stay there. A latency-aware feedback loop detects and corrects for the latency spike by shifting the traffic away from the slow server. This correction happens within a few milliseconds of the increase in latency. To conclude, we want to call upon the community to explore this emerging space of in-band feedback control at the server load balancers. Our techniques for in-band measurement with the direct server return is just a first step. Currently, we are evaluating our techniques on server real traffic traces, handling variations in the client think times, client packet transmission patterns such as spacing and service dependencies are some of the tasks in our future work. Thank you for your time. I can take questions now.
Hi, shooting from UC San Diego. So I want to ask a question that in all your examples, like you're kind of assuming there's a load balancer, right? What if we got like multiple of them? Like what if one of them is overloaded? Where are these data going to be? Like you're tracking all these like informations, right? And they're on the load balancer, right?
Yeah, we are measuring.
And what if the load balancer fails? Like how do you reconstruct these data when the failure happened? When there are multiple of them, maybe. And then when one of them fails, you might have to migrate that to other load balancer, or like how do you keep track of the information when the failure of the load balancer happens?
So one thing is that here, every load balancers will be receiving the traffic, right? So every load balancers, even if they are spread across the different data centers, they will be receiving the traffic, serving some clients from different regions. So what happens is like, even if one load balancer goes down, the other load balancers will be having traffic to the same server. So they will also be detecting the same kind of server lag in that load balancer as well. So we don't have to sync the information between the load balancers.
So essentially, these load balancers are keeping the same piece of information
Yes.
about the same group of server.
Yes.
Okay, thank you.
Yeah, hi, Coach Stace. I'm at Google. Yeah, so thank you for the talk, first of all. And like, I want to ask, what if you put the load balancer in a P4 suites? Like in that case, the replies that can go like back through the load balancer, and and you don't actually need like all of the fun stuff that you did, and they're very cool, but
yeah.
Isn't it much easier to do that? Like put like all the replies.
You don't have a direct server return.
Yes.
Yeah.
So if the direct server return is if not enabled, so the load balancer ideally can infer much more statistics about the server. So it would be easy to detect the server health by the load balancer. So this is means it can be applicable there also, but we don't have to infer like the batch. In that case, we can directly use a response and app. Yeah.
Okay, thank you.
Hi, I'm Divyanshu from UT Austin. So your solution, I think you assume that the clients are very close to the load balancer, right? So like in a data center, or I think if we go to a much larger scale than the prototype that we implemented, would it be possible that the responses that come, like the triggered packets that you send from the client to the load balancer, they get delayed a lot, and so the load balancer actually gets much idle information. So it would probably be much easier to like just for the servers to send additional triggered packets instead of this response latency, and to go the entire loop. Could just the servers respond to the load balancer and share whatever load they have?
Yeah. So the current settings where we were doing the first, the part of our project was like all the clients are like in the either nearby to the data center or within the data center, or so in that cases it makes sense like to do this kind of performance measurements. So like currently we are evaluating our traces on online traces, like where we see much variations of the traffic. So that is an ongoing work which we are.
Yeah, I'll be interested to look at the results.
Yeah,
Thanks.
thank you.
Thank the speaker. We have all the speakers come up also. We will be joined by. Okay. Srinivas is an assistant professor at. Why don't we go ahead and start?
Hi, I'm Venkat from MIT. This is mostly a question for Pratish, the second talk. Very thought-provoking work. Traditionally, HFTs have been kind of resistant to having any restrictions other than physics in how they do the trade. And this problem is as much a question of game theory as it is of computing network. So do you have some kind of a proof or an argument that the game doesn't fundamentally change if you go for this versus something where only nature restricts what HFTs can do?
So yeah, that's a very, very interesting question. So it kind of really depends on what kind of algorithms you are using. Like it doesn't necessarily mean that if I reduce response time or like ensure response time fairness, it means that you're gonna like a faster like participant is gonna make more money. All we are saying over here is that it's their responsibility that if I actually order faster participants trades ahead, that they win. So we do provide theoretical guarantees on, you are able to ensure response time fairness. Your trade might be generated. So, in any way based on a combination of points, all we are saying is that if you process this information quickly, we are going to order it correctly. Now, there are some game theoretic things that you can do. So a lot of work from the financial community is actually about, looking at these trades and, sort of ensuring maybe even a different form of fairness, which has nothing to do with speed. So there are typically things like that. But what we were essentially targeting is this like whole framework for speed trading. So people actually tried, flattening out that, you shouldn't compete on speed and everyone should have the equal opportunity. But this is how the game is. And maybe we were also thinking, taking examples from other real world things. So like online multiplayer games or something, where this whole concept just made a lot of sense. Yeah.
The other thing too, so you want to
have a lot of people
Also a question to Pratish. Hi, I'm KJ from Cornell. A very general question. So there is a general trend that people like to move the financial service into the cloud. And do you think once that completes, the general public can somehow enjoy this service? Like so that not just high frequency trading company like the people like me can join this market? Like do you have any vision to that?
Yeah, so I think I also mentioned this during the talk that currently only like 20-25 people can move to these exchanges. So they have a very they can only provide simultaneous delivery for a very small number of people. I think they typically can only support one switch. So anything which sits under one switch. So we expect that if you move to the cloud, everyone will be able to get response time fairness. And this is still about speed. We're also thinking about variants where we artificially restrict how much compute you get per trade. So it's not even like it's then just about having a better algorithm. It's not even about having better speed. Yeah.
Yeah, hi, this is Wei Tao from Arise and Google. I previously worked in a financial company, so I have a question about especially about the pacing. So actually, if different customers pace at different time, that will cause a problem also, because you can see I pace it like 1 second, 2 seconds, 3 seconds. Another one pace like 1.1 second, 1.2 second, 2.1 second, and 3.1 second. That will lead to a difference in terms of the time that you measure. This is unfairness.
So these, I'm not, it's very hard to ensure that like exactly same spacing happens.
Yeah.
So what we do is we actually prove some properties about how this pacing should look like. So typically the pacing properties look like this, that if data point X and X minus 1 are delivered to one guy 5 microseconds apart, they should be delivered 5.5 microsecond or 4.5 microsecond apart in the other case. So there is some difference in time over there, but the whole point is that you might not exactly get the same exact line of delivery, but if you're generating trade like using a particular data point and you're faster, then your trade will be ordered ahead. Does that make sense?
Yeah, so you mean like if I'm only 0.5 seconds faster, 0.05 seconds faster, I cannot exceed my other competitors. I'm only need to be like faster than pacing speed. I can be faster than others.
No, actually, this is like if your response time is lower, you will be ordered ahead.
Yeah, my response time must be faster than the pacing speed.
No. This is not the case. So your response time can actually be like it can exceed pacing. You can make decisions on like any data point that you want. So this was the whole point of this work, that you actually don't know how a trade was generated, whether you generated using like last data point, a data point before it, or maybe even like some data point which was delivered to you, I don't know, 100 microseconds ago.
I see.
There are proofs in the paper if you want to look at how this works.
Yeah. Okay. Yeah.
I think, to be honest, I think the question is similar to what Hari said. I think it was basically relative to the ordering to somebody that's responding to a subsequent update. Are you always ordering them ahead? Or is it being slower than the update time? Is that a penalty or not? But I think we'll take that offline.
I got a question for the compute-centric networking. So it's like a data flow programming like paradigm, right? And I'm kind of like skeptical about like how generic that can be like expressive. Like, can it express like loop? What if like got a loop inside that program? Can it express that, or like, yeah, and also like the separation of IO and compute. Can you care to elaborate more on that?
Okay, so I think the question is about how expressive our data flow, whatever system is. So I think, first of all, there has been many pre-existing works that's based on some sort of like dependency graph of computations like Spark, which is really, really famous. I think FixPoint is actually even more flexible than that, given that we have the ability of that these computations is able to generate new kind of computations as its output. So this is essentially like tail recursion, which I think like loop is for sure is able to be implemented this way, in the sense that the previous cycle of the loop is able to say that my output is actually the computation of the next cycle of the loop. So I think this is, representable in FixPoint. Then for in general about the separation of IO and compute, I think this idea all boils down to that we want all the dependencies of a computation to be locked down even before the computation starts. So for example, it will be similar that instead of like requiring computation to perform their executions on file system, we require them to be performing on like a certain commit of the Git repository, such that all the contents of file is already like pre-known to the computation even before it starts.
So is the data flow incremental, like the DD log thing, like the full stack SDN was talking about? Is this data flow like can support incremental updates of the data, or just like it needs to be a whole chunk of data is ready there and then just pass through the data flow to the end?
if I'm understanding correctly, I think the question is asking like whether the data itself is mutable, where I have to like always like create new data. So I think one really good thing about fixed point is that if all the computations are reproducible, then it's totally safe to like mutate existing data as long as you still know how to like compute them again if you want them to be back.
Okay, thank you. Hi, thanks for all the interesting work. I'm Will Sussman from MIT. And my question is about the load balancing work. If I understand correctly, the traffic, if it's forced back through the load balancer, then it's easy because the load balancer sees everything and it can perform internal calculations. So the problem here is that we're going around the load balancer and really wanted to go through. Why not create a virtual client at the load balancer that sort of assumes custody of whatever clients are going through it, so that the direct return sort of by overwriting the source address at the load balancer is forced back through, and then it can act as if it wasn't direct return.
Sure, yeah, hi. So the problem becomes substantially easier if you have both visibility into both directions of the traffic. But even there are some challenges with respect to like handling things like reliability, like reordered packets, kind of things being delivered, retransmissions and so on. But having said that, I think one of the main things that you're suggesting is if the load balancer takes over the session from the actual client, you're basically asking it to terminate the TCP connection, right? Which you could do, and there are load balancers that do that, like Nginx, like layer 7, you could configure it to do that. That's not a configuration that you can run for all settings, right? Like, so if you have a lot of traffic coming in from the outside world, especially DDoS traffic, it's preferable to run some of these things more kind of at the layer 4 level. So a lot of deployments end up having a layer 4 load balancer followed by a layer 7 load balancer, for example, where you would terminate the traffic. So I think the technique could work if you can take over the connection and basically split it. It's just that this is you still have to deal with situations where you cannot do that simply because of efficiency reasons and scale. And it's just really very CPU expensive to terminate connections, and it doesn't work all the time.
Hi, I'm Anup from SameView. I had a question regarding the financial exchanges. So could you speak a bit more about the motivation of moving it to the cloud? So I understand that, okay, NASDAQ does not want to manage the infrastructure, and it's better for them if a company like Microsoft or Google manages it. But why does this infrastructure need to be managed in the same way as public cloud is managed today? Why does it need to be multi-tenant? Why can't like these companies just build isolated infrastructure with the sole purpose of catering to financial exchanges? And so you can give latency guarantees, etc. Like, why does it need the same infrastructure need to be shared by other users for different use cases?
So I think one reason is cost. The other reason is scalability. We ideally want to extend the number of participants who can engage in such speed trading. And if you, we at least envision that thousands or, to thousands of participants will be able to compete this way fairly. I think there is also other reasons for moving to the cloud. So these market participants, right? They can only co-locate their algorithmic part to the exchange. They typically have their own like data centers like located close to these guys, which is actually deciding what algorithm they are running, right? So you can actually also move them to the cloud. Their cost is low, things like that. Yeah.
But basically you're saying is like, they can still move and still be isolated. So like, and that may not create like latency variation. So I can have these computation boxes co-located and still managed by a company like Microsoft, but it need not create latency variations. And so you may not need mechanisms for like creating fairness.
Yeah, I mean, if you do bandwidth reservations, you do in-network multicast, I think as you scale to the number of participants, it might be very hard. It's not even like you can build a setup which actually just houses this, but I think it'll still be a bit more complicated than that. And it'll actually require a lot of cost, right? And yeah, they already have a setup right now. If they want to just like use it, they can use it, but they still want these advantages. That's why they're considering moving. Yeah.
Thank you.
So Tal from UT Austin. So this is a question for the compute-centric networking. So if the goal is to keep track of the correctness of the program and to be able to tell if an intrusion alters the behavior of a program, I'm wondering if even the track record data generated by when running that program can exceed the amount of resources. So I mean the resources needed to even process those data can exceed that is needed to run the program itself.
Could you please repeat your question? So are you asking for like outputting tracing during the computation itself?
Yes, basically the output, the track record. I'm wondering if there can be an explosion of data there.
I don't think, first of all, I don't think FixPoint is trying to output like tracing data the same way as like, pre-existing record and replay tool. So we're not trying to say track down what are the system level function calls that all the computation are trying to make during the computation. So the more or less dependency is just like the dependency tree itself.
I see. Thank you.
Hi, this is Vital again. I have a question for the compute-centric networking. So do you think that if there exists a pipelining between computation and networking transfer, would that be increased complexity for your algorithm?
So I think the question, if I'm understanding correctly, is that there's like basically a parallel pipelining that you do the IO sometime and then in parallel you're doing the computation. Well, I don't think that is like, I think that's actually kind of orthogonal to what FixPoint is trying to do. So basically if like computation is already separated in the way that it first do all the like requests of like getting the IOs and then do the computation, it's probably like already something that FixPoint is trying to do now, then I don't think there's any issue of like parallelizing the IO with the compute itself.
I see. But my experience is that when I do the pipelining, the computation may also be slower in some sense.
I see, but I think that is probably more or less up to the scheduling decisions of these like computations.
Got it. Okay. Can I have another question for the trading?
Okay,
Yeah. Okay. Got it. Yeah. So my previous company will also do trading between different markets, like one in London, one in New York, one in Hong Kong. They will gather information from those three places and doing trading at 3 different places. So how the system can support this kind of trading?
So this is kind of interesting. Like you can ideally you can actually integrate multiple sources of data in this system, but that would really increase the latency of the system, because like the latency of the system is like max of RTT across all the participants. So I think if I understand it correctly, all these exchanges care about is that the participant, like whenever they collocate, they only ensure fairness with respect to their data. They don't care about like how other things happen. So we imagine that practically, if like multiple actually exchanges move to the cloud, they will put up separate sort of machines that will trade with each exchange, and they can communicate among each other, but it's very hard to guarantee like any sort of bounds on latency between these machines.
I see. Got it.
Hey, Rajat from Cornell. Can I ask a broader question? So I think all of you talked about problems, which to me, it seems like they relate to, Pratish talked about unpredictable latencies. Srinivas talked about unreliable transmissions and all of these. It seems to me that all these problems are somehow related to the best effort delivery model that data centers have adopted, which in turn seems to me an unfortunate consequence of how we learned things from the internet and brought to data center networks. And we are starting to learn or starting to live with this best effort model and starting to change things at upper level. I guess the question that I'm curious about is, have you all thought about what if we as academics try to go away for 1 second from deployment problems, right? And think about, suppose we want to not have best effort delivery model and we want some stronger semantics from the network. What semantics could the network provide that would help us alleviate or solve these problems in a more fundamental manner?
So at least for the financial exchanges work, if you can guarantee that the latency is bounded, then you can actually achieve simultaneous data delivery and ensure fairness. Or you can even do like bandwidth reservation things like that. You know, if I produce only this amount of data, it'll get through within this amount of time. Such properties might be great. Yeah.
Yeah, I think that's an interesting question, Rasit. Thanks. I think the network is only part of the problem in terms of the variation that we're trying to address in terms of controlling how requests can maybe reach the fastest server, for example. So there are lots of factors that are outside of the network here in terms of how the code on the application may have been written or the software is scheduled on the machine, how like you have layers of the virtualization stack that may be kind of moving things around and basically changing the performance of the server. So there are factors beyond the best effort. Even if you could provide a best effort network, we're basically removing one part of the problem in terms of like the different paths you might take to reach the destination. But fundamentally, you still have this issue that the machines themselves have application software that is becoming kind of, the applications are running for shorter and shorter time, and effectively guaranteeing their performance becomes harder at fine time scales. So I think like it could go some way forward in terms of making these problems like less relevant perhaps, but at least from current trends, it looks like the kinds of delays you might experience at the servers might actually sort of dominate the overall variation that you see for at least the latencies inside the cluster. Like just the network itself is not a significant component, and the server starts taking up a much more significant component because of the compute and kind of networks getting faster.
So can I actually add something more? Sorry, I'll just say one more thing. So, you know, you can make your network do more predictable things, but I think it's gonna do it like at a lower performance. And maybe the whole point is like, try to see with the best effort what you can get. I think you might be able to at the end get more performance sort of trying to deal with variance in best effort delivery or like in of that sort versus like something which is guaranteed to, yeah.
No, I was just going to make a point that I would love to see some result saying that something is stronger than best effort would mean performance degradation on an average somewhere else. Last question.
Michael Wetz, University of Oslo. A question for Batish as well. Would that, I mean, by the way, this is great work, but I'm wondering, would that create strange incentives in software design? This notion of fairness. I mean, I may have reasons to put my device to sleep for a while or to, you know, have a longer pause. Whenever I do that, I suffer, right? So I get an incentive to always do things immediately fast.
Yeah, so
and also upgrade my hardware to be even faster, right? than I may need to be just to be better served. Is that bad?
So in this entire system, we assume that release buffer is something that participants cannot control, and it's like in a trusted domain run by the exchange or the cloud. And when we actually prove in the paper that it's always in your best interest to respond as fast as possible. Yeah, so you can just think about it this way, like if you are taking like going to sleep, your response time is increasing, then you're going to get worse like ordering. That's it.
So if my hardware is slower than everybody else's hardware, then I get even worse served than everybody else.
Yeah, yeah. So
that makes my hardware even worse. So isn't that instant?
So if your hardware is worse, yes, you will be placed later.
Yeah. Okay. Yeah, I'm just trying to think up. You know,
so there might be other variants of
create
fairness.
Strange incentives in the way, or yeah, it's an interesting. Anyway, it's a very, very interesting work.
Let's thank the speakers.